I'm Dave Wagner. I manage the development of the Caesar capability at JPL and the deployment of this capability. Want to extend a welcome to JPL. Thank you for all being here. My part of the talk is tell you a little bit about what we've been doing at JPL as part of this Caesar effort. Here, I just want to kind of set context for what we've been doing. JPL likes to think that we invented systems engineering. We've been doing systems engineering for as long as JPL has been in existence. And I like to think that we have been using models as part of that systems engineering forever, because I don't think you can do engineering without models, okay? The idea of doing model-centric engineering, where the models really become the forefront of the engineering work, is something that has been evolving over time. And I like to think that, when we started introducing CAD and using those mechanical models as part of our engineering process, that was kind of the first step into our MBSE effort. But we continue to evolve that process and introduce more models and bring them closer to what we're doing. I call this early adopters epic. What has been a continuous process over time. And it continues today, right? We continue to prototype new tools, to prototype new methods, and try and get those integrated into our overall process. We're definitely not there yet, okay? We have a long way to go before we reach the ideal of what we all think MBSE should be, whatever that is, right? But we have made some progress along the way, and I will talk about a couple of different parts of that as we go through this talk. So my personal experience with MBSE really started before the Europa Clipper project, but it really started in earnest when we started the Europa Clipper project. Actually, when it was still a concept study. We had a small team that was all very much focused on the idea of trying to apply model-based methods to develop the concept for Europa Clipper. We started out building a SysML model in MagicDraw as one of the first things that we did. Very nearly at the same time, we started also developing a separate simulation capability, because the SysML model helped us to get our hands around what the thing is, but the simulation model was necessary to validate requirements against prediction performance of the system. Those two models developed largely in parallel across the early part of the life cycle. And in the end, when the project got funded and we actually started doing the formulation and system design in earnest, we found a lot of problems with MagicDraw, and it was hard to get 200 people to use the SysML tool, all at the same time. There was a lot of confusion about that. In the end, that tool was eventually dropped, and we developed we developed the requirements the old-fashioned way. There was a lot of value that came out of building that model and helping us understand what the architecture was. But in the end, there was just so many problems with the tool that we ended up using other capabilities. The simulation model, on the other hand, continued to evolve over the life cycle of the project. They continue using it today, and they plan to continue using that into operations to continue to calibrate power performance of the system and to validate that we can achieve the planned behaviors, the planned activities of the spacecraft against the performance capabilities of the spacecraft. That simulation model, by the way, was developed in a whole bunch of different languages and tools. It's a large federated simulation system that involves some Modelica, some custom-made tools, a lot of different capabilities. It has been described in several other papers, but I don't have time to talk about it here in detail. Around the same time, we developed in Magic Draw the capability to help us specify electrical connectivity in our spacecraft. This is a big system problem on our large spacecraft where we have lots of different electrical components. All the functionality needs to be connected up. It needs to be done at the system level. We actually built a tool in Magic Draw to do that. And we thought, this is pretty cool. This is a perfect application for, diagrammatic modeling. Users hated it. We deployed this on the Mars 2020 project. Users hated it because they basically couldn't find anything. You have thousands of connections that need to be specified. Every connection has many different details, and trying to find those in diagrams was very problematic. So they didn't like it. All of this, and at the same time, the MBSE project was established essentially to fund small prototype research and development tasks in the area of model-based systems engineering. We funded a lot of prototypes. We wrote a lot of conference papers, but very little of that work ever reached a technology level that it was actually being used on projects. Okay. So that leads me to, in 2017, the management looked at what we were doing in MBSE and said, how would it be if we just refocused this effort rather than funding a lot of prototypes? Let's fund a more directed effort to develop something and get it actually used in production. And that required a close alignment with subject matter experts, with projects. So we got partnered with the Europa Clipper project that was ready to start doing this harness specification at that time. We got partnered with the line organizations who do the work. They were very eager to get some help because they knew that they had a really hard problem to solve. We had a prototype, the one that I mentioned that we did in Magic Draw, to start with. And we wanted to develop a capability that would be reusable on multiple projects and would actually help to make this this work less error prone, okay, to get a more consistent result out of it and get a more consistent, have less rework in the harness engineering. And also to develop a task-focused user interface that would make it easier for the engineers to do the work. The diagram here is the Caesar workbench that we developed. I'll talk a little bit more about that in a later slide. So we thought a lot about what would be the right platform for developing this capability, and came to the conclusion that we want to focus on the information that we're trying to capture in this model, and that's where we kind of found our way to the web ontology language, to the semantic web set of larger semantic web capabilities. And OWL with description logic specifically, we want to be able to, OWL itself is a little bit complicated for certainly for systems engineers to deal with. So we wanted to initially develop vocabularies in OWL that would describe our methodology, develop user interface, which we developed in Eclipse. So the Rosetta IDE is an Eclipse-based application for developing the user interface. We wanted to integrate continuous integration into this process also, so that we could continuously run validation and transformations of the model, because we kind of recognized right off the bat that there is some information that the modelers are going to want to be able to deal with through the user interface. But most of the people, most of the consumers of this information, most of the reviewers of the information don't really want to model it in the tool. They want to see derived reports and other review products that that kind of present the information in a way that they can more easily consume. So the ecosystem that we came up with, I already partially described this. The ontological modeling language, OML, is basically our wrapper for web ontology language. It provides us with a concise way to express models in OWL and OWL2DL. And it implements some design patterns. Nicholas will describe this in detail later. The vocabularies, we developed a layered set of vocabularies that reflect our design methodology. There are some lower level foundational layers to that vocabulary that are likely to be very reusable, things like the metrology vocabulary for units and quantities. But as we get higher up into the vocabularies, they more specifically reflect our specific system engineering methodology and then project-specific specializations. And the nice thing about this is that we can layer them in this way so that we have parts that are more reusable and parts that are specifically customized to the project's needs. The fact that we have a Java API for OML allows us to develop a whole suite of tools that are part of what we've shared in OpenCaesar to do transformations of the OML, the transformations of the information from OML to OWL, and then other tools that we use to merge models, to run semantic reasoning, and to put it into Sparkle database, for example. That's part of also in the OpenCaesar tools. And then the Rosetta IDE is the Eclipse-based user interface that we develop on top of that. Aaron will talk a little bit later about OML Vision, which is our, at this point, still kind of incomplete intended replacement for Rosetta. So it's more of a web-based application that doesn't depend on Eclipse, and it's purely web-based, intended to be an editor eventually. And then, like I said, because in the foundation layer, it's just OWL, there are many free and existing and COTS tools that we can use in the semantic web to help us transform and analyze the model information. And OML is also compatible with doing change control in Git. And so we heavily rely on using Git, and we have GitHub Enterprise at JPL. for doing change control of the models. Next. There we go. The application that we have developed, we're using Caesar as a specification front end. The initial application for Caesar was this specification front end for our harness design process. And when we did this on Europa, we developed reports, and then the harness design people actually took those reports and went off and did their design. We have subsequently adapted this on the sample return lander project so that we actually now have a connected pipeline. So we developed a structured JSON output from our Caesar model that can, and then an adapter for the Capital Logic electrical CAD tool that we use to actually do the design, so that we can now transform the specification model from Caesar, ingest that into the ECAD tool to guide the design. We haven't quite got to the point where that can synthesize the design, but we're very close to that, okay? But at least what we have now is that the designer can actually compare the design that they are working on with the specification and validate consistency. So this has helped a whole lot. This has enormously helped smooth out our harness design process, which, you know, for a lot of companies, harness design might be kind of a secondary thing, but in spacecraft, this is a really huge deal because harness makes up like 15% of the mass of a spacecraft, and that's a big deal. So we really need to get this design, get our hands around the design, at least get an estimate of the mass of a harness at a very early stage in our big projects, especially. So this has been a really big deal. I will mention that you know, we have Europa Clipper used our tool, the Psyche spacecraft used our tool. Psyche has retired their capability now because the spacecraft has been built and launched. We plan to launch Europa Clipper later this year, but as I mentioned, they plan to continue using it because they extended the capability to model power performance, and they want to continue to use that in operations. Sample Return Lander is our current customer, and we're working actively with them to extend the capability to add flight software behavior properties into the model and transform that into products that flight software can actually interpret directly into flight software. But with the funding challenges that we have as a federally funded organization and the potential delays with the Mars Sample Return Program, there's a lot of uncertainty in what we're going to be able to accomplish here in the next year or so. There are a whole lot of lessons that I could talk about. I probably won't have time to talk about all of these, but the first one is, I think, the most important. By the way, there was a really good article in the latest INCOSE journal summarizing lessons learned over a large number of research papers. And they agree with me that this first rule is the most important. This first lesson is the most important. Know what you're going to do. If you're jumping into MBSE, have an idea of what you're trying to do with it. And this applies to any kind of modeling, I think. Figure out what questions you need the model to answer. Answer those questions. Okay. If you're doing anything else, you're wasting your time. Okay. And the corollary to that is the slippery slope of modeling, that it's really easy and fun to build up big models. That's what we did on Europa. And when we did an assessment several years into the project, we discovered that 99% of the content that we had in the model was junk. Meaning it was there, but it had no reason to be there. There was no analysis that it was connected to. Okay. No useful analysis that it was connected to. And that's why the model became so slow and hard to use, right? The task-focused user interface, I think, is really important. This was really a big deal for our users to get a user interface that was focused on the particular task that they had to do. They didn't have to understand how the model really works underneath. They didn't even really have to understand the vocabularies, although intrinsically, you got to understand fundamentally what you're trying to say, right? But they didn't have to understand the syntax of the model in order to do the work that they needed to do. And then I think, just in the interest of time, the last one is also, I think, a very important lesson that, as I said, on Europa Clipper, we used many different tools and a large federated simulation modeling capability that had, we did use SysML to capture a lot of descriptive information about the system. Eventually, we translated a lot of that useful part of the descriptive model into Caesar, and we continue to maintain that descriptive information in Caesar. But there are some expectations or assumptions from people about MBSE that, oh, I just want a turnkey tool that does everything for me, and I don't think that's going to happen. Okay. So going forward, we're at the cusp of where SysML version 2 is about to appear in the marketplace, and there are a lot of questions about how that's going to affect the landscape. Questions with me too, I don't know. But that's one of the things that we want to investigate. We expect that SysML v2 will have fixed a lot of the problems that we had in our experience on Europa Clipper. I still think that many aspects of system engineering require specialized vocabulary. Every project is different. Every organization has different methodology and different problems to deal with. And to me, in my experience on projects, even when we developed what we thought was a very general JPL methodology vocabulary, we found that projects still have the need to specialize certain things just because there's information about their design that's going to be unique to their design that they need to be able to capture and analyze and validate. Modeling across different levels of abstraction is a particular challenge. We dealt with this in our harness specification pipeline in having to describe the specification at one level of abstraction and map that to design at a much lower level of abstraction. We have a whole lot of lessons about how we did that I don't have time to talk about here today. But it's possible, but it's complicated. And then, as I mentioned, our fiscal environment for this year is challenging. We are optimistic that we're going to be able to continue working with the sample return lander, but nobody knows what's going to happen right now. So I have time for a couple of questions. Can you turn on your microphone there so that we can hear you?
Hi, Michael Halverson. You mentioned that the Psyche mission was phasing out their MBSE practice because it had already launched. This indicates that model-based operations, or AMOS, is not considered under the purview of Caesar. Do you have any plans to integrate Caesar with AMOS?
Integrating Caesar with the ground data system, probably not, but we do have other, I'm gonna, I have a very expansive view of what MBSE is. So we have other test tools that are, I believe, model-based test tools that we're developing that are integrated with the ground system and are being used on Psyche in operations. The only reason that we're not using Caesar in Psyche operations is because they opted not to build their power performance model in Caesar at the time. And so they only used it for harness specification. Their harness was built, so they were done.
Would you say that the utility of model-based methods in operations is a future goal? I would say that the jury is probably still out on whether or not it'd be useful. It hasn't been tried all that much.
Yes, I started out in the ground system many years ago, and so I'm very much aware of the need there, but because model-based methods in operations involve designing a system, you can't just tack that on later on, after launch. It's a very complicated problem to get those model-based capabilities built in from the start, when we're building the spacecraft.
Thank you.
If you can speak to the Clipper, because Clipper is going to use it into operations.
Yeah,
speak in the microphone.
Yeah. So, and I mentioned that Clipper is going to be using Caesar into operations. There's a microphone over here.
Hi, my name is Hanumantrao Kannan, Professor of Systems Engineering at UAH. My question is about one of the points you mentioned here, how do we manage these local language conventions, right? So one of the issues I see with systems engineering is the lack of a foundational theory, like other domains. If you think about fluid dynamics, there is foundational theory. And if you build models, simulations based on that, we have to respect that, right? But systems engineering, we are trying, but we don't have that yet. So is there any push within JPL for such an effort? And a follow-up question is, especially with respect to systems engineering concepts, how were they defined in OpenCaesar?
Okay, it's a big question, and I'm actually out of time, and I don't want to step on Hassan's talk. My 10-second answer is, it's very difficult to generalize in this area. We focused on what is the specific problem that we need to solve, and that made it successful. That's probably the simplest way to answer that.